The purpose of this video is to help you in understanding some of the equations that you can find in this weekly material. So the first equation that you will encounter is the equation for convection. So this one is just a review of the formula for convection that we have. So this one is your heat transfer due to convection, while Q prime prime is the heat flux. So Q dot heat transfer, Q prime prime is heat flux. When you multiply heat flux by the surface area, we can have heat transfer. That's why this Q heat flux is just equals to this value here, H times Ts minus T infinity. Our Ts is the surface temperature, T infinity is our fluid temperature. So the temperatures can either be in degrees Celsius or Kelvin. So it won't matter because this is just temperature difference. Another equation is this one. So the reason why Q convection is equals to Q conduction, because we don't consider here any other heat that comes in or comes out of the system. So that's why whatever heat that goes out in a material or a solid material is just equal to the heat that is basically surrounding that material. So that is equals to negative K, or the negative of thermal conductivity, multiplied by the temperature gradient. So this one is temperature gradient. It means the temperature at any point along the flow. So that's temperature gradient. So when you substitute for the value of convection, we know that convection is H delta T, or Ts minus T infinity. That's why we have this equation here. So just put Ts minus infinity in the denominator from this equation, so we can have the value of the convection heat transfer coefficient in terms of that thermal gradient. So how about this equation? This is just the average or the mean convection transfer coefficient for a particular surface. So we will not use this much because we will use the derived version of this equation. So how about this one? So this one is our shear stress. So we know that shear stress is just force times force per unit area. So your Newton per meter squared. The shear stress is just equals to the product of, this one is our dynamic viscosity mu, and then the velocity gradient. So ganina natin temperature gradient. This one naman is our velocity gradient. Mu here, or U here is velocity, while mu, this is dynamic viscosity. So that is the general equation in finding the shear stress. So viscosity is expressed in terms of the relationship between two viscosities. We have kinematic viscosity and then the dynamic viscosity. So kinematic viscosity is the V here, and this one, the mu, this is our dynamic viscosity. So the relationship is in terms of the density rho. The wall shear stress is derived by evaluating this equation here, and then we have this equation. So our CF here represents, this is a non-dimension number. This is our friction coefficient, or the skin friction coefficient. This one is our density. V is the velocity in meter per second. So if you're going to find the force is just stress times the area. So that's why we have, if you multiply this one by area, we can have the force, or the friction force, the friction coefficient. So this is an important parameter in heat transfer since it is directly related to the heat transfer coefficient. some important dimensionless numbers are, first is your usselt number. So the usselt number is just the product of the convection heat transfer coefficient H, LC, which is the characteristics length in meter, K is the thermal conductivity. So this is derived from the ratio of convection to conduction. The usselt number is important in finding the value of the heat transfer coefficient H. So later on, we will see that for laminar flow, for different types of flows, the usselt number will also vary. And then this one is your frontal number. So frontal number is just a product of mu, which is our dynamic viscosity, Cp, which is our specific heat, over the thermal conductivity K. So this is available in tables, the value for frontal numbers of different types of fluid. Then we have Reynolds number. So Reynolds number is an important dimensionless number because it will help us understand what will be the type of flow. So the Reynolds number is just equals to, can be written as in this form, but when you don't have the value for kinematic viscosity but you have the dynamic viscosity, then you can use this equation. So we'll learn that our V is just mu over rho. That's why we have this equation. V is the velocity, LC is the velocity. So this table shows us different dimensionless groups. So important here are the Biot number. We have the usselt number. Grashof number is also important. Frontal number, Reynolds number. So we will use some of this later on as we go through our discussions. So the table is found in the book in Copera. So you can check that book. So kanina we encountered the term critical Reynolds number. So the critical Reynolds number is equals to 5 times 10 to the power of 5. So it is critical because when the Reynolds number is greater than 5 times 10 to the power of 5, the flow will become turbulent. But when it is less than, the flow will be laminar. So these equations here are the equations for a steady, two-dimensional and compressible flow with constant properties. So when the flow is one-dimensional, so you can delete the other terms. So these are the continuity, the momentum, and the energy equations. So let us see how to use this equation later on in an example. The equations that you find here from this diagram, these are the boundary conditions and deriving these equations here. And then this set of equations here, these are the equations for a parallel, steady, and compressible flow over a flat plate. So we have parallel, steady, tapos incompressible flow. So if the flow is parallel and steady, so we can use this set of equation in finding the thickness of the velocity boundary layer, the thickness of the thermal boundary layer, the local usselt number, and the local friction coefficient. So this equation is your drag coefficient, CD. The drag coefficient is helpful in finding the value of the drag force. So the drag force, if you're going to rearrange the equation, is just equals to the CD times 1/2 rho V squared A. This another important equation is our film temperature. This is used to evaluate the properties of the fluid, like thermal conductivities, the frontal numbers, the value of mu or V. So we will evaluate at the film temperature. So when the temperature of the surface and the temperature of the fluid is known, you must get the value of the film temperature, and then from that temperature derive these properties of the fluid. So in the next video, we will proceed with external force convection, some of the equations that you will often encounter in solving external force